Superconductors possess an almost mystical quality, defying the fundamental laws of electricity that govern our everyday world, where resistance is an inevitable barrier to efficiency and power. Discovered in 1911 by Dutch physicist H.K. Kamerlingh while experimenting with mercury cooled to near absolute zero, these materials exhibit zero electrical resistance, allowing current to flow indefinitely without energy loss. This magic isn't sorcery but a profound quantum mechanical phenomenon that challenges our understanding of matter at the atomic level. Superconductors not only expel magnetic fields, a trait known as the Meissner effect, but also enable feats like levitating magnets or transmitting power across vast distances with perfect efficiency. From revolutionizing medical imaging to promising a future of limitless energy, superconductors stand at the intersection of physics, engineering, and innovation, unveiling potentials that could transform society. As we investigate their properties, applications, and the breakthroughs on the horizon, we peel back layers of resistance, both literal and metaphorical, revealing a world where the impossible becomes routine, and the magic of science propels us toward an electrified tomorrow. At the core of superconductors' enchantment lies their extraordinary properties, which emerge when certain materials are cooled below a critical temperature, Tc. In this superconducting state, electrons pair up in what's known as Cooper pairs, according to the BCS theory developed by John Bardeen, Leon Cooper, and John Schrieffer in 1957. These pairs move through the lattice of atoms without scattering, bypassing the collisions that cause resistance in normal conductors. The result is infinite conductivity. A current once started in a superconducting loop can persist for years, theoretically forever, without any applied voltage. Equally mesmerizing is the Meissner effect, where superconductors become perfect diamagnets, actively repelling magnetic fields from their interior, leading to phenomena like magnetic levitation. Imagine a magnet floating effortlessly above a superconducting disk, defying gravity as if by magic. This is no illusion but a direct consequence of quantum mechanics at play. Conventional superconductors, like niobium-titanium alloys, require cryogenic temperatures around 4 Kelvin, -269 degrees Celsius, achieved with liquid helium, limiting their practicality. However, the discovery of high-temperature superconductors, HTS, in 1986 by IBM researchers Georg Bednorz and Alex Muller, using copper oxide ceramics like IPCO, yttrium-barium copper oxide, with Tc up to 138 K, brought the dream closer to room temperature. These properties not only defy resistance but also open doors to manipulating quantum states, making superconductors indispensable for probing the fundamental building blocks of the universe, and engineering solutions that could eliminate energy waste in our power-hungry world. Delving deeper into the structure and mechanisms of superconductors reveals a symphony of quantum effects that orchestrate their resistance-defying behavior. In the BCS framework, phonons, vibrations in the crystal lattice, mediate the attraction between electrons, overcoming their natural repulsion to form Cooper pairs. These pairs condense into a macroscopic quantum state, behaving as a single entity that glides through the material unimpeded. For high-temperature superconductors, the mechanism is more elusive, possibly involving spin fluctuations or stripe phases in the cuprate layers, where copper and oxygen atoms align in ways that enhance electron pairing at warmer temperatures. The critical temperature marks the threshold where thermal energy disrupts these pairs, reverting the material to a normal resistive state. Superconductors also exhibit a critical magnetic field and current density beyond which superconductivity breaks down, leading to Type I and Type II classifications. Type I abruptly lose superconductivity in strong fields, while Type II allow partial magnetic penetration through flux vortices, making them more robust for practical use. This intricate structure enables applications like superconducting quantum interference devices, SQUIDs, which detect minute magnetic fields with unparalleled sensitivity, used in everything from medical diagnostics to geological surveys. The magic here is in the quantum coherence, where billions of electrons act in unison, creating a state of matter that blurs the line between the microscopic and macroscopic, challenging our classical intuitions and inspiring new paradigms in condensed matter physics. One of the most transformative aspects of superconductors is their wide-ranging applications, turning theoretical magic into tangible technological marvels that permeate modern life. In medicine, superconducting magnets form the heart of magnetic resonance imaging, MRI, machines, generating strong, stable fields to produce detailed images of the human body without invasive procedures. These magnets, often made from niobium tin, operate at liquid helium temperatures, enabling non-ionizing scans that have revolutionized diagnostics for diseases like cancer and neurological disorders. In particle physics, accelerators like the Large Hadron Collider, LHC, at CERN rely on thousands of superconducting magnets to bend and focus proton beams at near-light speeds, facilitating discoveries such as the Higgs boson. Transportation sees superconductors in maglev trains, like Japan's Yamanashi test track, where magnetic levitation propelled by superconducting coils allows vehicles to glide at speeds over 600 km per hour with minimal friction and energy loss. Energy transmission is another frontier. Superconducting cables, piloted in projects like the Amper City in Germany, can carry up to 5 times more current than conventional lines with negligible losses, potentially reducing global energy waste by billions of kilowatt-hours annually. Even in computing, geosys and junctions, superconducting tunnel barriers, enable ultrafast, low-power circuits for quantum computers, promising to solve complex problems intractable for classical systems. These applications showcase how superconductors defy not just electrical resistance but also the limitations of inefficiency, paving the way for a more sustainable and advanced society. Looking toward the future, the potential breakthroughs in superconductivity hold the promise of even greater magic, with room temperature superconductors as the holy grail that could redefine energy, computing, and beyond. Scientists are pursuing materials like hydrogen sulfide under high pressure, which achieved superconductivity at 203 K in 2015, or carbon-based compounds like graphene derivatives that might operate at ambient conditions. Advances in materials science, including machine learning algorithms to predict new superconducting compounds, accelerate this quest. Imagine a world where power grids transmit electricity across continents without loss, slashing carbon emissions and enabling widespread renewable integration. In fusion energy, superconducting magnets could confine plasma more efficiently in reactors like ITER, bringing clean, limitless power closer to reality. Quantum technologies stand to gain immensely. Fault-tolerant quantum bits, qubits, based on topological superconductors could resist decoherence, ushering in an era of practical quantum computing for drug discovery, cryptography, and AI. Space exploration might benefit from superconducting propulsion systems, while everyday devices like lossless batteries or hyper-efficient motors could become commonplace. However, challenges persist. Achieving stability at higher temperatures, scaling production, and understanding unconventional mechanisms remain hurdles. Yet, with ongoing research at labs like those in the US Department of Energy or Japan's Riken Institute, the magic of superconductors inches toward ubiquity, potentially solving global issues like climate change by defying the resistance of outdated technologies. Recent discoveries and innovations continue to unveil the evolving magic of superconductors, bridging theory with real-world impact and hinting at untapped potentials. In 2020, a team at the University of Rochester reported superconductivity in a carbonaceous sulfur hydride at 287.7 K, 15 degrees Celsius, under extreme pressure, inching closer to room temperature and sparking debates on reproducibility and scalability. High-throughput screening methods have identified promising candidates like lanthanum hydride, while advances in thin film deposition allow for flexible superconducting tapes used in wind turbines and power lines. The discovery of superconductivity in twisted bilayer graphene in 2018, dubbed magic angle graphene, revealed how subtle atomic arrangements can induce pairing at relatively high temperatures, opening avenues for tunable quantum materials. In applications, the deployment of HDS cables in South Korea's grid demonstrates practical viability, reducing urban power losses. Gravitational wave detectors like LIGO incorporate superconducting sensors for precision measurements, while emerging fields like neuromorphic computing explore superconducting synapses for brain-like efficiency. These breakthroughs not only defy resistance but also push the boundaries of what's possible, with implications for everything from ultra-fast data centers to advanced sensors for dark matter detection. Yet, mysteries linger: the exact pairing mechanism in HDS, the role of impurities, and the quest for ambient pressure, room temperature variance keep the scientific community enchanted, driving relentless pursuit. The magic of superconductors extends beyond the lab, influencing our cultural and philosophical views on innovation, and the defiance of natural limits. In popular culture, they evoke images of futuristic utopias, from levitating cities in science fiction to the zero-resistance metaphors for effortless progress in self-help literature. Philosophically, they challenge deterministic views of physics, showing how quantum subtleties can yield macroscopic wonders, reminding us that resistance, be it electrical or societal, can be overcome with ingenuity. Their study has spurred interdisciplinary collaboration, blending physics with chemistry, engineering, and even biology, as seen in bio-inspired materials mimicking natural low-resistance pathways. Economically, breakthroughs could democratize energy access, reducing inequalities in developing regions. As we anticipate missions like the European Space Agency's JUICE probe, which uses superconducting tech for Jupiter exploration, or the potential of superconducting quantum networks for secure global communication, the horizon glows with possibility. The unknown in superconductivity isn't a void but a canvas, inviting humanity to paint a future where energy flows freely, computations race at quantum speeds, and resistance is but a relic of the past. Superconductors, with their ability to defy resistance and harness quantum magic, continue to captivate and transform our world. From their foundational properties and diverse applications to the breakthroughs that promise a resistance-free future, they embody the triumph of human curiosity over natural constraints. As research unveils more of their secrets, the magic of superconductors not only powers our technologies but also illuminates the path to sustainable innovation, challenging us to envision a world unbound by loss and inefficiency. The journey is ongoing, but each discovery reinforces that in the realm of science, true magic lies in defying what was once thought impossible.